Okay.
So, hello. We have now Daniel, who's going to talk to us about the deadline scheduler. Daniel Bristot is a Red Hatter. He's an SME at Red Hat.
Oops. Okay. Hi. As I said, I am. I'm Daniel. I came from the pizza planet. I'm in Italy. I live in Pisa, and I work as a kernel engineer at the support engineering group. And I work mainly with the real-time related products like Red Hat Enterprise Linux for real-time. And as my hobby, I do a PhD in Brazil, and I'm doing part of my research at the Scuola Superiore Sant'Anna in Italy, where the SCAD deadline were developed, both the theory and the code. And my research area is obviously real-time. So let's start a little bit with some theory to be able to compare schedulers, and then we will go to the SCAD deadline implementation and how to use it. So what are real-time systems? Our real-time systems are those systems with deal with external events from real world, and those events have some timing constraints, and they must the response for those events must to be delivered within the main time constraint, that is the deadline. So even on HPC or on kind of processing, we have some kind of max latency we must respect. The difference between the HPC and real-time is that if your system starts to deliver response after the deadline, your system really loses its value. The response there's no value on the response if it arrives after a known deadline. So the correctness of the system depends not only on logical stuff, but also in the timing behavior of the task and the timing requirements. So on a multitasking real-time operating system like Linux, a real-time scheduler is responsible for scheduling tasks in a predictable way, in such a way that all the responses are delivered within the deadline. And on the scheduling theory, there are two religions. The fixed priority religion, where every task has one fixed priority and all its activation, all its jobs have always the same priority, like we implement with the real-time scheduler on Linux, the FIFO scheduler. And we have another religion that's the dynamic priority schedulers, which we have one that's a job level fixed priority scheduler. That means that one task doesn't have a priority, but each job, each activation of a task has its own priority. And the next job will have a different priority. And in this case, Linux implements the deadline scheduler. That means that the task with the earliest deadline will be served first. So early deadline first scheduler. Well, in the real-time theory, the tasks are represented by the timing constraints. Doesn't matter the language, doesn't matter the processor, just the timing constraints. And by turning these timing constraints into variables, we can do some math and compare schedulers to see how good is a scheduler comparing one each other and analyzing the properties of the schedulers. And another point about real-time is that we are always thinking in the worst case. Doesn't matter if the average case is better. The only thing that matters is the worst case. Like the running time of a task. We don't care if the task in the average is better than another. We care if in the worst case, the runtime of a task is bounded, it's known, and you can compare with other algorithms if the worst case is shorter or not. So to be able to do this math, we need some patterns of the task. The task must follow some patterns. And one known pattern is the activation pattern, that one task may be periodic if it arrives at every period, like after 3 units of time, the new job will arrive we can have sporadic tasks when we have this minimum arrival time in between each task, but it can be bigger than the period arrival. And we can have, in the absence of a pattern, we have a aperiodic task. We also have a constraint about the deadline, when the task will deliver the response. And in the deadline task model, we have an implicit deadline when the deadline is equal to the period. We may have a constrained deadline when the deadline can be shorter than the period. And we can have arbitrary deadline when we have a deadline that it's after the next period. So let's do some exercising then to be able to compare schedulers. So let's suppose we have a system with 3 tasks. The task 1 runs, in the worst case, for 1 unit of time at every 4 units of time. And the deadline of the task is equal to the period. And we have task 2, which consumes 2 units of time at every 6 units of time. And the task 3 with 3 units of time at every 8 units of time. If we divide the worst case execution time by the period, we have the load of the task. And the sum of the load of these tasks is less than 1, which means that my processor is not overcommitted. Like, I will have this task running for 95% of the time. I still have some band to guarantee stuff. So using this task set, let's try to schedule them using a task level fixed priority scheduler like the sched_FIFO. And we arrange the tasks using rate monotonic. That means that the task with shortest period will receive the highest priority. It's optimum among all the task level fixed priority. So I'm using the best way to schedule these tasks. And it turns out that the task 1 and task 2, the task 1 arrived, all tasks arrived at the same time. Task 1 will start to work. Then it finished, the task 2 will start to work. And then the Q3 will be able to run for you 1 unit of time. But while it was running, the task 1 arrived and it will start to run. And then the task 3 will start to work again. And the task 2 arrived, it's preempted, and boom, we missed the deadline. So the fixed priority scheduler is not able to schedule these tasks on a uniprocessor while meeting all the timing requirements, obviously. And on the job level fixed priority scheduler, let's take one example with the schedule rule that is the task with the earliest deadline will be served first. So in this case, you can see we don't have a red block here. We are not missing deadline. But just to explain the rule, like we have these 3 tasks, they were released at the same time, and task 1 will run because it's the earliest deadline. Then the 2, then the 3 will be able to run. They are at the same deadline, and you can pick any one. Like if the one preempted, it will still 1 unit of time here, because the Q2 deadline is in front, like this is the early deadline. So it turns out that it's mathematically proven that the early deadline scheduler, the early deadline first scheduler is optimal for uniprocessors. It means that the early deadline first can schedule any task set that is schedulable on one processor. And so that's good. We just need to use EDF. And moreover, we don't lose time selecting the priority of the tasks. You just put the parameters and the scheduler will do it for us. Like we don't the highest priority tasks. We don't keep switching tasks very often. Like we have other schedulers, optimal schedulers, that do it like prefer. But, well, we always have a trade-off. Although EDF guarantees the deadline, it doesn't guarantee you the minimum latency. When you have the fixed priority scheduler, the highest priority task will be delivered with the minimum latency. And when you want just-in-time computing, that EDF is not good because of it, even though the deadline is always granted. So, and moreover, the complexity to implement this scheduler, it's O of log n, and you can implement the fixed priority on O of 1. But wait, it's O of 1 because the user already selected the priorities, and a user to select priorities can be as hard as O of n factorial. But the implementation is faster, I'd say. But in any case, when you arrange your tasks with the task with the shortest period, with the highest priority, you have an optimal scheduler for a fixed priority, but you can schedule less tasks than while running the deadline scheduler. And there is, when you don't have a complete predictable system, the EDF is not as predictable as the fixed priority. So, when you have one task that runs for more than its set runtime, or when you have an overloaded system, you can have the domino effect on deadline scheduler. And in this case, when one task runs for more than its runtime, or one task misses its deadline, all other tasks can lose it, can miss their deadline. On the other hand, on the fixed priority scheduler, only the tasks with the lowest priorities will miss their deadline. The highest priority task will never miss their deadline. So, okay, let's put some complexity here. I was talking about uniprocessor scheduling, and now we will start to talk about multi-core scheduling. So on multi-core scheduling, we have another problem that's not only how to prioritize the tasks, but also how to put the tasks on the CPUs, like the allocation problem, how to allocate tasks on CPUs. And for this case, we have some kinds of schedulers. We have global scheduler that will manage a single queue of process and will distribute over the processors. We can have a clustered scheduling when you have some domains of scheduling, global on the CPUs which it manages, but in a small set of CPUs. Or you can run partition scheduler when you say, okay, this schedule will manage this CPU, this scheduler will manage this CPU. And here you have a system with many, like Unicore's system. And we can have arbitrary affinities when you say, okay, a task can run on this and this cluster and this partition at the same time. So, just an additional, deadline scheduler is a global scheduler, but we can implement all this other stuff with configuration, and I will talk about it later. So, multi-core scheduling adds on the math side a lot of anomalies. And one anomaly is that there's no way to say what is the worst case to dispatch all the tasks. And this turns the development of a real-time scheduler a little bit harder. And many things are working in progress yet because of these anomalies. Like for uniprocessors, the theory is stable, everything is there. But the state of art of a multiprocessor or multi-core scheduling is still happening. Like the development is still happening. There is another anomaly, that's the Hall's effect. That it's like it adds a contradiction. Like if you have, for example, a system very load. I have a system with M CPUs, and I have M tasks, and these tasks run for all the period. Like the tasks run 100% of time. I have a completely full system, and it is schedulable. Even if I have a global scheduler, it will put one task on each CPU, and the system will be schedulable. So let's turn things better. So I will have just small tasks, very small, M small tasks, with the deadline a little bit earlier than the old big task. But, well, in this case, we don't see the anomaly. The system is still schedulable. But let's add a little bit of load. Let's put just one of those big tasks on the system. The load of the system is lower than the load of this system. But this system is not schedulable anymore because this task has an early deadline and will delay the big task for this small amount of time, and it will miss the deadline. And this is the Hall effect. That's why Woodcore scheduling is many times it's pessimistic. Well, so far I was just introducing the characteristics and the problems we have while working, or maybe better, the benefits of the deadline scheduling and the problems we might have using deadline scheduler. But now let's talk about the deadline scheduler we have on Linux and how to deal with these problems. So the sched deadline is a global, all CPUs, or deadline first scheduler. For sporadic tasks, the task can arrive in a periodic fashion, like at every period, or sometime after the period. And the deadline, it must be implicit or constrained. The deadline must be equals to or smaller than the period. And in these cases, we can schedule using the sched deadline. And the sched deadline receives 3 parameters. The runtime, that is the amount of time that task needs from the CPU to be able to finish its work, the amount of CPU time the task needs. The deadline of the task, and the period. So the sched deadline schedule will guarantee for this task that it will receive the runtime at every period within the deadline. So the task will have its CPU time to run within the deadline. And then we can guarantee that the task will finish before the deadline. Well, so starting how to deal with some problems. It's very hard to specify the runtime of a task on Linux because the processor is very unpredictable and we have tasks influencing on the execution time of another task. So it's hard to say the worst case execution time for a task on Linux on an Intel processor with a lot of parallelism. So in order to avoid that a task with a runtime that was not correctly estimated, to avoid that this task run for more than its runtime, causing the domino effect I told, the sched deadline adds a protection with a constant bandwidth server. The constant bandwidth server guarantees that each task will receive the runtime, and if a task misbehaves and tries to run for more than its runtime, the task becomes throttle. So explain a little bit the CBS, the constant bandwidth server. At every period, a task will receive the amount of runtime. And while running, the runtime is consumed. And if the task calls the sched yield system call, it will be put to sleep and will be awakened in the next replenishment. So we will implement a periodic task. If the task never suspends itself, in the end of the budget, it will be throttled and will be able to run again only in the next replenishment, in the next period. So this helps to avoid the domino effect. And if the task goes to sleep during its activation, if it's awakened before the deadline, it will be able to run again until the deadline. And but if it's awakened after the deadline, it will be throttled and it will start work again in the next period. But we have this here because I found a bug on it and we are working fixing it now. So all this complexity just to arrive to one command line. That's how you set the parameters for a task. So you can use chrt, just saying that, okay, I have a video processing tool. I will process 60 frames per second. And to process one frame, I need 5 milliseconds. And to be able to schedule this, I will have a period of 16 milliseconds. So at every 16 milliseconds, my command will receive 5 milliseconds of CPU. And well, to be able to release the next task before this period, I need to deliver the result for this processing before the period, like within 10 milliseconds, allowing the next task that we receive this frame to run within this deadline. Well, and you can also set these parameters in C using this system call set_attr. But this system call can fail. Like on the fixed priority scheduler, you can put as much task as you want, because it didn't try to guarantee that task will meet the deadline, because it doesn't have the deadline abstraction. But the deadline scheduler will start to reject tasks when it notices that it will not be able to do the work. So in this case, the deadline scheduler will start to accept new tasks when the real-time tasks are try to use more than the allowed time for real-time tasks on Linux. So by default, on Linux, because of these CTLs, the real-time tasks can run for 95% of time. That's configurable, and the default is this. Well, so if the system is lower than 95% times the number of CPU, it will start to reject. But this is just a necessary but not sufficient test. What does it mean? Well, let's explore one thing, the house effect. If I have, in this case, with this guarantee, I cannot avoid the House effect, because I can have one task running all of the time, like running the 95% of time in the CPU, and more than m other tasks running for a short period. And then the m earliest deadline task will be scheduled, and sometimes it can happen that my big task will have the deadline really late, and all other m tasks able to run, and it will preempt this big task, and it will start to miss the deadline. And why? Why do developers choose to not use one admission test to avoid tasks missing their deadline? They choose it because this test is too pessimistic. We have one admission test that guarantees you that all tasks will be scheduled and will run within the deadline. Sorry. Even in the presence of a big task. But it is too pessimistic. In the worst case, if I have more than on a system with m processors, if I have more than m tasks and one big task, the maximum I can schedule is one processor. Like, I will not be able to schedule more than the load of one processor without missing the deadline. So global scheduling is really bad while dealing with tasks with a large utilization without meeting their deadline. So, well, so how to deal with big tasks while running in the sched deadline? How to put more load on a system in which I have a task with a high load? Well, the sched deadline is global, so it will suffer with the house effect. And a task on the deadline scheduler cannot set its affinity, like it will run on all the domain. But it's possible to break the system on smaller root domains and schedule deadline tasks inside the smaller root domains, enabling us to have a system with like I can break my global system into 2 clusters of deadline tasks and other partition it. Like I can have one sched domain here, which will sched all deadline tasks on these 2 CPUs, and I can set one sched domain here to schedule just this CPU. So how do we do that? We do that using CPU sets. It's hard to set these. It's not easy, and people are working on sched deadline to make this more flexible, but that's how we do it nowadays. We need to create, for example, I will create 2 CPU sets. One with a single CPU to put my big task and let it run alone there, and a cluster of CPUs with all other CPUs. So I need to disable load balance on the root domain. That's an odd restriction. And I go to the cluster, I set CPUs, the memory. I set it exclusive because I cannot have the overlapping of root domains with deadline tasks. Deadline task must run one scheduler for one CPU. I cannot have 2 schedulers managing one CPU. So I need to set it exclusive. And then I move all my tasks to this cluster, and I can start all my small deadline tasks here because I will not suffer the house effect. And then I go back and create my partition, the CPU set it exclusive, set just to run on the CPU 0, and I can run my big task here. And so we suffer from the Hall effect because we are global, but we can work around it managing the root domains using CPU set. And okay, the presentation was way shorter than when I thought, but well. When should I use the deadline scheduler? What are my requirements? First the question is, do I have timing requirements? Because you need to know the timing requirements. You need to know how often a task is awakened and how much CPU time it needs and what is the deadline. Well, if you don't have these parameters, it's really hard to start to use the sched deadline because you don't know how to set the system. You need to know this. But we have a special case which I will talk later. So, okay, I have the requirements. That's good. So am I more concerned about the deadline of the tasks or about the latency of the highest priority task? If I care about the latency of the highest priority task, it's easier to provide this with a FIFO scheduler than with a deadline scheduler. But if I'm really concerned about deadline, it's hard to guarantee that a task on the FIFO scheduler will meet the deadline because it does not even have the idea of what is a deadline. While on the other hand, we have the notion and we guarantee that we will schedule things within the deadline. And do I have a large number of tasks? That's another good thing because you don't need to care about the priority of tasks on sched deadline. And if you think on allocating tasks on processors and setting the right priority for this task on the processors with a fixed, in a fixed way, like a fixed priority, you have an NP hard problem. And if you have a larger number of tasks, it will be really hard for you to set the appropriate priority for the task. So deadline scheduler really helps on it. But we have the aperiodic case, like my algorithm is not discrete, it's like continuous, and I have a formula that provides me the guarantee that if I receive this amount of CPU time at every period, it will be enough for me to schedule all the tasks I want. So if you don't know the periodicity of your task, but you know how much CPU time you need to accomplish it, and it's enough for you, you can use the sched deadline just to provide the queue CPU time over the period, using just a constant bandwidth server. That's for such kind of tasks, say periodic tasks. And do you want to use a base loop with sched deadline? Please don't. you will cause the house effect in the first time. And the sched deadline is it has a static priority higher than the real-time tasks. So it will try to first pick deadline task, and if there's no deadline task, it will try to pick a fixed priority task. If you run Q over P, you will just run forever, and you will delay everything in the system, and you will delay migration threads, and you end up having a hog system. So please don't. That's not your use case.
You said that you can use just 95% tops, so this should help, right?
Yeah, this should help for non-real-time tasks.
Yeah.
But you might delay the real-time tasks with fixed priority because you reach the end of the line.
Yeah, the deadline is like priority 0.
Yeah. Oh. Can you repeat the question on the microphone? Oh, okay, I got it. So, if my deadline task will use only 95% of time, I will still have 5% of time to run other tasks. That's correct, but that's for non-real-time tasks, CFS tasks, not fixed priority tasks. And then you will delay fixed priority tasks. And like migration thread are fixed priority tasks. That's it. But yeah, that was a good question. So, okay. Deadline scheduler and the real-time kernel. So, these are two different things. The deadline scheduler is scheduled tasks. And it schedules tasks in the same way, both on the real-time kernel and in the non-real-time kernel. So, what are the benefits of using the real-time kernel? Well, the real-time kernel resolves the priority inversion problems. A priority inversion takes place when a lower priority task is running in a condition in which it don't allow the highest priority task to start to run. For example, if the task is with preemption disabled, like my write back. The write back function for my block of block disks is running. It disables the preemption to have a better throughput, and it will start to delay the activation of a high priority task. That's what the real-time kernel resolves. In the non-real-time kernel, we don't have a guarantee of how long a priority inversion will be. For example, we can have a 3 milliseconds priority inversion, 10 milliseconds priority inversion. And so if I have a 10 milliseconds priority inversion, I cannot guarantee that a task will give the response within 10 milliseconds because it can suffer a delay of 10 milliseconds and then we will start to work. Like, I cannot guarantee. And that's the benefit of running both together. The real-time kernel guarantees you max latency of 150 microseconds, which allows you to give a short deadline for a task, like 1 millisecond. The task will start to run after 150 microseconds, and I will still have all the rest of time to run my computation. So this is one benefit of using the sched deadline with the real-time kernel. But you can run, if you don't care for so tight deadlines, like if your deadline is 1 second, there's no reason to use a more predictable kernel. There's another issue that's unbounded priority inversion, but it's in this case, if you have tight deadlines, you need actually to use the real-time kernel. And you can find, So you can find more about the comparison about the real-time kernel and the non-real-time kernel on this link. And actually, this presentation is the resumed version of an article which explains how to use sched deadline. I was working on it. I will put this article on Rails blog on next week probably, explaining in details and how to use it and more stuff. So what is next on the sched deadline? We are actually working now on a group protocol. It's not a group bootloader. It's a runtime reclaiming protocol, agreed runtime reclaiming protocol that will turn the deadline scheduler more flexible. For example, if I have a task with its runtime, assigned runtime, it will not be able to run more than its runtime. But if I have just this single task, I may turn the system idle. And well, why not use this idle time to run deadline tasks? Why not use this spare time using deadline tasks, running deadline tasks? So the grub will turn the runtime more flexible, and it will allow a task to run to get more CPU time as long as it doesn't interfere on other deadline tasks. Luca Beni is a professor at Escola Superior Santana, where I'm continuing the PhD. He's implementing this, and he will soon release another version of this patch. I'm actually testing it. And there is a lot of discussion about trace points to explain the behavior of a deadline task. I submitted patch with trace points, but Peter Zylstra said no. And there is a lot of discussion because he don't want a trace points specific for a scheduler. It wants it to be generic for all scheduler, just one sched switch trace point. And the people at I forgot Matthew Desnoyer's company is working on it. LTT Energy people. He submitted one patch set. It's there for me, for people to review. I need to review this, but I didn't review because I was doing the slides. And we need to add more scheduling statistics for people to know how much runtime the task actually consumed, if it missed the deadline, if it doesn't miss the deadline. Tommaso Cucinotta, that's a professor at Scuola Sant'Anna, is working on it right now. And I had another patch set rejected by Peter Zylstra because, well, we have the RT throttling on the real-time scheduler, which prevents the real-time tasks to run for more than 95% of time. It throttles and let the non-real-time tasks to run. And then I submitted a patch saying, okay, if I don't have no, let me introduce the problem, man. I didn't finish the problem. So this 95% will be, the task will be throttled once they reach this 95%, even if there is no other task to run, if the system goes idle. So you end up missing CPU time. You could run for more than it if you are not starving any other task. And then I submit a patch asking, hey, if I have nothing else to run, let the real-time tasks running. But Peter Zylstra said no, because what we really want is a hierarchical scheduling with deadline scheduler in the base, and you will put non-real-time tasks inside this deadline server, and then you provide the guarantee by scheduling the deadline server and not by throttling the real-time. This will turn things on things on CPU sets probably more easier to provide rarity throttling guarantee because we actually don't respect the things there. But it turns out that this will be really complex, mainly because we don't accept arbitrary affinities. Okay, on how many? You mean I will not have time to explain this, but this will take some time. And in a way, okay, currently we cannot say the affinity of a task on deadline scheduler because it's global. And we need to respect this rule to respect the guarantees of scheduling. But there is an article from Bjorn, from MPI, MPI SWS Institute in Germany, which he gives some proofs that you can actually do arbitrary affinity on global scheduling, deadline scheduling, but this will also take some time and everything is under development. Woodcore real-time scheduling is something that is still a problem for academic stuff. Then it will take some time until this become reality. But on the other hand, it's challenging and we have nice stuff to do here. And that's all, folks. Questions? Oh, one question.
So, can you tell me some tools that will help me with estimation of how much it will take, or to do some initial estimations?
Okay, the question was, is there any tool to help me to estimate runtime or period? Actually, you need to use tracing tools like perf or ftrace. Set the sched wake up to see how often a task is awakened, and set the sched switch to see when the task is start to run or go to sleep, and then you make some mathematics using BC, and you'll be able to estimate. But that's the state of art. Like the deadline, the trace points for sched deadline would allow us to print how much runtime a task still have when it goes to sleep. So you could estimate using just one trace point, but this is still under development, and you have to use imagination with perf and sched and ftracing. Oh, we have more questions than deadline scheduler users here. No, in the world, like we don't have 2 deadline scheduler users in the world yet. The house problem, explain it again. Okay, he asked me to explain the house effect problem again. Yeah, it's tricky. Okay, so here I have a system with m tasks, 1 task per processor. And this task runs forever. This is, the load of my system is 1 for each processor, 100%, 1, and times the number of processors. We have the load of m. That's huge load, right? And then let's turn things better. Let's say I will have the minimum runtime for a task, like 1 unit of time for m tasks. My load here, if I put everything inside the same processor, will be smaller than 1. It will be the minimum times m. And this system is schedulable. Obviously, it's schedulable. But here we find one anomaly. We will increase the load of the system, but the system will not be as load as this. So I'm still reducing the load of the system. The load of my system is 1, like this task running all the CPU time. It's still 1, plus m, the minimum time. So the load is obviously, you can see in the draw, that's is lower than this. But in this case, as these m tasks have the deadline earlier than the big task, they will be scheduled first. Because one property of the sched deadline is that the m earlier deadline tasks will run first. So it will correctly schedule all the m small tasks. But by running this time, it ends up pushing the start of the big task. And it will push it for after the deadline. And then I will miss the deadline of the largest task. You might say, hey, but I can put this task on the other CPUs. So you can guess this because we humans are clairvoyant. We can see things in the future, but the scheduler don't. The scheduler is not seeing that the task will miss the deadline there. So we have how to deal with this? Create a CPU set to put all the m small tasks and confined on the other CPUs, and then put the big task isolated. That is the example that I gave with CPU sets. Is how to turn this system schedulable. I put all m tasks on a part of the system using CPU sets, and let this task running alone, poor task, in the CPU 0. Yeah.
Well, if the scheduler knew the runtime of the big task, it would see that it had to schedule it immediately.
But that's another scheduler. 0 lacks the first scheduler, which have other properties and then it's always like you have one other property good, but you have another worst case, and the only optimum scheduler for this class of tasks is using pfair, which I slice the task in very small slices and try to schedule them. But then the overhead is imperative. Like you have to have a lot of timers, a lot of migrations, and a schedule switch, and you lose your CPU time.
Last question. So what you suggest in this case is to make two groups and use the small ones in one group and the big ones in the group.
Yeah. That's the example I gave in the, yeah.
So I'm playing with Realtime KVM.
Okay.
I'm actually interested in, right now Realtime KVM pretty much assumes that you're running on isol CPUs where the actual real-time, for example, schedule deadline can be used in VPS.
Okay.
Make sense, or would it be possible at some point to calculate schedule deadline parameters for the actual guest vCPU processes?
That's a more complex. It's really hard to. Okay. I will repeat the question. So, you have a box, and you want to run a virtual machine on this box, and this virtual machine will have a vCPU, and this vCPU should run alone on a processor. And you want to guarantee that this vCPU will receive all the CPU time from the real CPU, avoiding any latency, because if you have a latency, you may miss network packages, for example. And this vCPU, actually, they wanted to run this the more time as possible, like run forever, correct?
Correct, but the thing is, I don't really want to run any isol CPUs. Like in perfect case, I wouldn't have to isolate it, but I could run it with schedule deadline.
Okay. Problems of using schedule deadline on this case. You will always delay all other tasks. And currently, the state of art is that there's no way to completely isolate one CPU on Linux. You always have something to run there, like a key worker that will be scheduled indirectly scheduled there, and so on, and migration threads, and so on. So, in this case, if you want to give all the CPU time for this vCPU, the best thing you can do is try to isolate all the stuff from there, and the state of art will be able to have a no hertz full, only the tick of no hertz full at every second. That's the best you can do. But in this case, it doesn't matter if you use schedule deadline, CFS, or real-time FIFO scheduler. You receive the CPU time because you isolated it. You might not want to use the isol CPUs, but you will reach the same results, like trying to set affinity and so on. Okay, it turns out that the best you can reach in this scenario is the same of using sched FIFO. So yeah, you can reach the best. That's the same of sched FIFO, and if you really isolate your CPU. Because if you run a sched FIFO or sched deadline forever, you end up postponing other tasks that might be scheduled there and causing problems. So in the best case, in the worst case, you have okay, I'm finished within the deadline. So it turns out that doesn't matter which schedule you use. You might want to use the FIFO scheduler in the real-time kernel to avoid unbounded priority inversions. That's another subject involving mutexes and priority inheritance. But the best you can reach is the same of sched FIFO, including unbounded priority inversion. And there is one problem with sched deadline, which are the control of priority inversions. With sched deadline is not as stable as everybody wanted it to, because the sched deadline doesn't have a priority, it have a deadline. And so the priority inheritance will not be inheriting a priority, but the deadline of the task. And there are no issues about it. Peter Zuster even mentioned on the last Realtime Summit, I'm running out of time and I was throttled. I'm sorry. Thank you. That's it.
Continue your conversation.
Yep.
Yeah.
You can continue the conversation outside. Just mute it from there. So that we can pull it off without.
Thank you very much. I'm sorry we have to be in this.
No, yeah, yeah.
Okay. Yeah.
You have a very good friend in Brazil.
Oh, Rafael.
Yeah.
Actually, are you from Brazil? No, you're
Yeah.
from.
No, I'm living in Italy. I
Oh,
have
yeah.
dual citizenship,
Yeah, yeah.
but I used to live in Brazil.
Yeah. Actually, he's a very good friend of mine. He
Yeah,
comes up
yeah.
and visits me, and
They say if you met Larry Woodman, say hi.
oh yeah, well, good. He's him and they really good guy.
Yeah, I really
enjoy.
like it.
He comes up and visits us, and we
Yeah, and
play.
and he likes math, and we have a discussion about math and Linux kernel together.
Yeah.
It's nice.
Good answer to the last question, too. I'm with Larry. My name is Shaq.
So how do we do?
We run the perf group.
Yeah.
I run the perf group at Red Hat.
Oh, nice.
So we've been doing DPDK, KVM Runtime, all that
Yeah,
fun
I
stuff.
am on their meeting, and I knew the problem beforehand. That's why I have the.
That was nice. 'Cause that would have been the same. I almost asked that question. I knew it's a long answer, but you did very well. That's all. Very.
I never say, okay, don't do it. I say us.
So
And then they continue using and say, okay, let them find their luck. Nice.
Very nice talk. So, affinities. So even if you put things into CPU sets, and then allow you to use schedule deadline within the set, is that
But how come
reasonable? Because then you can hold the schedule deadline.
Okay, hold on.
Or C group, yeah, whatever.
Oh, just drag it over.
But you cannot isolate the
Where?
scheduler within the system set. So isolate the
Open as a
scheduler.
presentation in a separate window, so you
Or
will see
yeah, or
text
just
here.
Just shrink that down, Larry.
start the presentation.
No, don't do a full screen.
Yeah.
No, right here.
This guy?
No, the middle. And then drag that over to the other screen.
But then you will see your.
Here we go.
Yeah.
Well, and then he can mirror it,
You
right?
have to
Or
start
do
the presentation.
So how do we? What do we do?
you want to do the presentation first? However
Yeah,
you
well,
want.
sit,
Let's
you
bring
know,
it
put
back
it in.
and start the
Put it in
slideshow.
slideshow.
It will most
Put it
likely
in slideshow.
I'll let you grab it.
Just put it in slideshow.
Yes, that's window then.
Do you mirror them both, though?
How do we?
Just grab it again, yeah. Sorry. Now slide it back.
How do I do that?
Push and
It
pull.
won't go.
Yeah, here.
You drive.
I'm going to get
You
that.
can grab it from
It's
here.
not working.
Just move the cursor.
Oh, okay. Move it over that way.
Exactly.
Put it
You're saying put it in full screen first?
No, put it in
guys?
slideshow.
And I'll do both.
Yeah.
Yep. Here we go. Have the clicker.
You got a clicker? There we go. Put that in one of your USB.
Here.
And the USB is off.
Is it up or down?
Want a water?
So we have time cards. If you like 10 minutes at the end, we'll call you 10 minutes before.
Okay. I'll watch this thing very closely. And, this is the